In many situations, we'll want to measure how fast a quantity is changing. And a very common way to do that is by calculating the average rate of change of a quantity. So if you have if we have this function f of x and we want to know how fast it's changing, we have to have some idea of what range of x values we're talking about. So suppose that we want to measure the rate of change of this function over an interval from x equals a to x equals b. So in this case, to calculate the average rate of change of f of x, what we'll do is we'll just figure out how much f itself has changed, that is, how much the outputs have changed, and divide that by how much the inputs have changed. And the order here is important, so we always have the end value first and then the beginning value second. Okay, so we'll just divide by the change in the values of f divided by the change of the input values that we're using. No doubt you've seen this formula before. Average rate of change is such a common thing to need to calculate that you've probably seen this formula for years. So let's use this formula to calculate the average rate of change for this particular function over the interval from 1 to 4. So here we don't have a formula for this function f of x, but we have its graph, and that's almost as good. So we're going from the x value 1 to the x value 4. And remember, points on a graph are of the form x comma f of x. So to use this formula for the average rate of change, we are going to need to know so 1 is playing the role of A and 4 is playing the role of B. So we know A and B, we're going to need to know f of A, which is 1, and f of B, which is 4. Right? So we're going to need f of 4 minus f of 1 over 4 minus 1. To get these values, well, these values are going to show up as y values on certain points on this graph, right? For the x value 1, f of 1 is going to show up as the y value of the point on the graph corresponding to the x value 1, and that point is right here. Right? So this point is 1 comma 4, so this is 1 comma f of 1. Right? So f of 1 is actually 4. And by the same token, over here, this point 4 comma 2, this is 4 comma f of 4. Right? So this graph is really telling us what the value of the function is at these two x values. So f of 4, that's 2, and f of 1, that's 4. Over 4 minus 1, that's 3. So this looks like it's minus 2/3. Okay, so if you have a graph for a function, or if you have a formula for a function, you can find the average rate of change of the function over any interval just by using this formula. No doubt a familiar calculation. Well, you may have noticed when we did this calculation, right, we had these 2 points. We calculated f of 4 minus f of 1 over 4 minus 1. But this is exactly the slope formula, like this, y2 minus y1 over x2 minus x1, for the 2 points that we're using here. Right? The first one was 1, 4, and that's playing the role of x1, y1. And the second point was 4, 2, and that was playing the role of x2, y2. So when you find an average rate of change, what you're really finding is the slope of the line that goes through the 2 points on the graph. So this particular line, when we have a line that goes through 2 points on a graph like this, we'll call this a secant line. It doesn't really have anything to do with the use of the word secant from trigonometry. It's a different sense of the word secant. So a secant line is just one that goes through 2 separate points on a graph. And when you find the slope of a secant line, you're really calculating the average rate of change of the function between those 2 points. Now this has a really nice interpretation if our function happens to tell us a position. So suppose that we have this, suppose we have some object that is moving back and forth along a line, and we can measure its position just by assigning position numbers along this line here. So positive will go one way and negative will go the other way. Then a function might tell us the position of this object as a function of time. So let's suppose that this function, f of t, tells us the position of this object in meters after t seconds. So let's interpret the average rate of change and what the units for it would be. So if we're going from, say, A to B, so maybe A is over here somewhere and B is over here, the average rate of change, that's going to be the change in the function divided by the change in the input variable, which is t. So this is f of b minus f of a over b minus a. So let's think about this. Let's think about the units here. So these values, b and a, those are times, right? Because they're along the t-axis, they're values for the t variable. So these are in seconds. Okay, and when you subtract two quantities that have the units of seconds, you get a quantity in seconds. So this denominator has units of seconds. What about the numerator? Well, remember this function, it's giving us a position in meters. So this quantity here, f of b, this is in meters. And same thing for f of a, that's also in meters. And when you subtract two quantities that are in meters, you get another quantity that's in meters. So this rate of change, the units for it are meters per second. And that makes sense because the rate of change of a position is what we usually call velocity. And, you know, if you're measuring distances in meters and time in seconds, then velocity ought to come to us in meters per second. And sure enough, that's what this formula spits out. It gives us meters per second. But in fact, this is a more general phenomenon. No matter what the units for your inputs and outputs are, our average rate of change so the units for an average rate of change, so the units for average rate of change are always output units, meters in this example, divided by input units, seconds in this example. And that always happens because this difference in the numerator is always going to have the units, the same units as the output, whatever f is producing. And in the denominator, the units will always be the units for the independent variable, the input units. So no matter what your function is measuring, this average rate of change formula always produces these units. And of course, that's always a slope, right? In this graph, the input units, input units are on the horizontal axis, output units are on the vertical axis. And so when you divide output units by input units, well, that's a slope, because a slope is the vertical change divided by a horizontal change, but that's output units, change in output units divided by, or change in output divided by change in input. Right. So every rate of change will have units that we can find quickly just by taking the quotient of the units for the inputs and the outputs.